Chapter 2, exercise, example 2.1. Two charges 5 into 10 raised to minus 8 coulomb and minus 3 into 10 raised to minus 8 coulomb are located 16 centimeter apart. At what points on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. We discussed such problems, and in that we discussed this thing, potential, that is the scalar quantity. So we will get 2 points where the resultant potential will be 0, 1 point that will be between two charges, and another point that will be outside it. Okay, now see, two charges given to you, Q1 that is 5 into 10 raised to minus 8 coulomb and Q2 that is minus 3 into 10 raised to minus 8 coulomb. And these two are separated by 16 centimeter. So charge Q1, charge Q2 and are separated by 16 centimeter. Suppose one point in between these two, that is at distance x centimeter from charge Q1. So from charge Q2, it will be at 16 minus x centimeter, where the resultant potential becomes 0. Now, at position P, we can write the equation for the resultant potential, that is k q1 upon x plus k q2 upon 16 minus x, and that is equal to 0. Substitute the values of q1 and q2 and then take k common, take it on right hand side, will be cancelled. So 5 into 10 raised to minus 8 upon x minus 3 into 10 raised to minus 8 upon 16 minus x. Q2 is negative charge. So here this negative sign will appear. Take 10 raised to minus 8 common, take it on right hand side. It will be cancelled. Then we will get 5 by x, that is equal to 3 upon 16 minus x. Now solve this one. You will get answer x equal to 10 centimeter. Means the point P between these two charges where the potential is 0 is located at 10 centimeter from charge Q1, or we can say it is at 6 centimeter from charge Q2. Clear up to this? Now another point where the potential is 0, that is outside two charges. Suppose another point is R where the resultant potential becomes 0. That point is at a distance y from charge Q1. So it is at a distance y minus 16 from charge Q2 as shown in the figure. Now at position R, we can write k q1 upon y, the potential due to q1, plus k q2 upon y minus 16. So the resultant potential, that is 0. So equal to 0. Now again take k common, take it on right hand side, will be cancelled. Substitute the value of q1 and q2. Again 10 raised to minus 8 will be cancelled. So resultantly we will get 5 by y minus 3 upon y minus 16, that is 0. So we will get 5 upon y equal to 3 upon y minus 16. Now solve this one and calculate y. You will get y, that is 40 centimeter. Means another point where the resultant potential is 0 is situated at a distance 40 centimeter from charge Q1, or you can say it is at 40 minus 16 means 24 centimeter from charge Q2. Clear to all of you? Example 2.2. A regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. Simple thing. See, for regular hexagon, the center that is at the same distance from each vertex. Suppose the distance that is r. Now, here first we have to calculate the potential at the center due to any one charge, then multiply it by 6. Now, charge at each corner, that is 5 microcoulomb, so that is 5 into 10 raised to minus 6 coulomb, and the side, that is 10 centimeter. But here in the figure you can see this thing. For hexagon, when we think about the center, then center will be exactly at the distance equal to the length of the side, so that will be also equal to r, so that is 10 raised to minus 1 meter. Now, potential at the center due to any one charge that we can give by kq upon r. Total 6 charges are there, so multiply it by 6. So resultant potential, that is 6 times kq upon r. K, that is 9 into 10 raised to 9, q that is given to you 5 into 10 raised to minus 6 upon r, that is 10 raised to minus 1 into 6. Now solve this one, you will get the resultant potential at the center of hexagon. Clear? Example 2.3. Two charges 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. A. Identify an equipotential surface of the system. B. What is the direction of electric field at every point on this particular surface? Now see, charge A, that is 2 microcoulomb, and B, that is minus 2 microcoulomb. Okay. So, as shown in the figure, if these two are separated, then at the center, the resultant potential will be 0. So here, if we imagine a plane passing through the center perpendicular to the line joining to these two charges, then at each and every point on that particular plane, the potential will be 0, because each and every point that will be at the same distance from plus 2 microcoulomb and minus 2 microcoulomb. So net potential, that will be 0. So we can say the equipotential surface is perpendicular to AB and passing through the center. Now, second question, what is the direction of electric field at every point on this surface? So we know this thing. In theory we discussed electric field at each and every point on the equipotential surface, that is perpendicular to the surface, and electric field that is from positive to negative. So here the direction of electric field will be perpendicular to the equipotential surface, and that will be from A to B. Clear to all of you? Example 2.4. A spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 raised to minus 7 coulomb distributed uniformly on its surface. What is the electric field? A. Inside the sphere. B. Just outside the sphere. C. At a point 18 centimeter from the center of the sphere. Now, radius of the sphere that is given to you 12 centimeter. So that is 12 into 10 raised to minus 2 meter. Now, charge on it, that is Q equal to 1.6 into 10 raised to minus 7 coulomb. First, we have to calculate the electric field inside the sphere. But in theory, we discussed this thing for a spherical conductor. Inside it, at any point, the electric field that is 0. Not only for the sphere, but for any type of conductor inside it, the electric field that is 0. Then just outside the sphere. So just outside the sphere means we can take the distance from the center, that is R. So electric field E, that is KQ upon R square. K, that is 9 into 10 raised to 9. Q, that is 1.6 into 10 raised to minus 7. R, that is 12 into 10 raised to minus 2. Square of it. Solve this one. You will get the answer. Then third one. At a point 18 centimeter from the center. So this point is outside the sphere. So again we can use the equation KQ upon R square, where R, that is the distance of that point from the center. Now electric field E dash, that is KQ upon, here the distance is taken as X, so X square. K, that is 9 into 10 raised to 9. Q, that is 1.6 into 10 raised to minus 7 upon X, that is 18 into 10 raised to minus 2 and square of it. Solve it, you will get the electric field at 18 centimeter from the center. Clear to all of you? Example 2.5. A parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. 1 picofarad, that is 10 raised to minus 12 farad. What will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6? Now see, the capacitance of capacitor that is given to you 8 picofarad, that is 8 into 10 raised to minus 12 farad. Now capacitance of capacitor that is given by the equation epsilon 0 A by D. Now here the distance between the plates is reduced by half. So distance is made D by 2. Okay. And then after, the dielectric substance having dielectric constant K is introduced. So we can write the capacitance for the separation equal to D by 2. That is C dash equal to epsilon 0 A upon D by 2. And when the dielectric substance having dielectric constant K is introduced, the capacitance becomes K times. So finally our equation becomes a C dash, the new capacitance, that is equal to K into epsilon 0 A upon D by 2. So resultantly we can write 2K epsilon 0 A by D. But epsilon 0 A by D, that is our original capacitance which is given to you. So here introduce it, epsilon 0 A by D, that is C. So C dash, the new capacitance, that is equal to 2Kc. So 2, K the dielectric constant that is given to you 6, and C, that is 8 into 10 raised to minus 12. Solve this one, you will get the new capacitance. Clear? Example 2.6. Three capacitors, each of capacitance 9 picofarad, are connected in series. A. What is the total capacitance of the combination? B. What is the potential difference across each capacitor if the combination is connected to a 120 volt supply? Now see here. Three capacitors, each one that is with same value 9 picofarad, are connected in series. So we can say C1 equal to C2 equal to C3, that is equal to 9 picofarad, and say that is C. Now total capacitance of the combination. So when each capacitor that is with the same value, then C total, that is, as per equation C by N, we can write C by 3, that is 9 by 3. So 3 picofarad, that is 3 into 10 raised to minus 12 farad. Now here the combination is connected with 120 volt supply. So V, that is equal to 120 volt. Now V, that is V1 plus V2 plus V3. But each capacitor that is with same value. So potential difference across each one, that will be same one. So we can write potential difference across each capacitor. Suppose it is V dash, then resultant V, that is 3V dash. So V dash, the potential difference across each capacitor, that is V by 3. So that is 120 by 3 equal to 40 volt. Clear? Chalo. Example 2.7. Three capacitors of capacitance 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel. A. What is the total capacitance of the combination? B. Determine the charge on each capacitor if the combination is connected to a 100 volt supply. Very simple. C1, that is 2 picofarad, C2 that is 3 picofarad, C3 that is 4 picofarad. And it is connected with the supply voltage of 100 volt. Now in parallel combination of capacitors, we know the resultant or equivalent capacitance that is given by C1 plus C2 plus C3. So C equal to C1 plus C2 plus C3, that is equal to 2 plus 3 plus 4. So that is 9 picofarad. So that is 9 into 10 raised to minus 12 farad. Clear? Now we want to calculate charge on each capacitor. So we know this thing in parallel combination, potential difference across each capacitor, that is the same one, and capacitance of each one, that is given to you. So charge on first capacitor, that we can write Q1 equal to C1V. C1, that is 2 picofarad, so that is 2 into 10 raised to minus 12 farad into voltage 100. So your answer is 2 into 10 raised to minus 10 coulomb. Then charge on second capacitor Q2, that is equal to C2V. C2 3 picofarad, so that is 3 into 10 raised to minus 12 into V100. So that is 3 into 10 raised to minus 10 coulomb. Then charge on third capacitor Q3, that is equal to C3 into V. C3 4 picofarad, so that is 4 into 10 raised to minus 12 into V100. So your answer that is 4 into 10 raised to minus 10 coulomb. Clear? Example 2.8. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 raised to minus 3 meter square and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. If this capacitor is connected to a 100-volt supply, what is the charge on each plate of the capacitor? Simple thing. Area of the plate that is given to you 6 into 10 raised to minus 3 meter square. Separation between two plates that is 3 millimeter. So it is 3 into 10 raised to minus 3 meter. And the supply voltage with which the capacitor is connected, that is 100 volt. Now capacitance of parallel plate capacitor, that is C equal to epsilon 0 A by D. Simple, substitute the values. Epsilon 0 that is 8.85 into 10 raised to minus 12. Area of the plate that is 6 into 10 raised to minus 3 upon the separation D that is 3 into 10 raised to minus 3. Solve it, you will get the answer. Clear? Then after,
Yes, sir.
charge on each capacitor, or sorry, each plate of the capacitor, that is Q equal to CV. So as per that we can write Q0 that is CV, whatever the value of C here obtained in terms of farad, substitute that value here and then multiply it by 100. You will get charge on the capacitor itself is the charge on each plate. Clear? Example 2.9. Explain what would happen if in a parallel plate capacitor given in exercise 2.8 with air between the plates. Each plate has an area of 6 into 10 raised to minus 3 meter square and the distance between the plates is 3 millimeter. A 3 millimeter thick mica sheet of dielectric constant 6 were inserted between the plates A, while the voltage supply remains connected, and B, after the supply was disconnected. Means initially you insert the mica sheet when the supply is connected one, and second time when the supply is disconnected, after that you introduce that mica sheet. In both the cases, what happens that we want to calculate. Now see, when 3 millimeter mica sheet with dielectric constant 6 is introduced, the capacitance that will be K times than the initial one. So value of initial capacitance that we calculated in the previous example, that we have to substitute here, multiply it by dielectric constant, its value that is 6 given to you, then solve it, you will get the capacitance. Now if supply voltage is connected, now your new capacitance that is C dash, so charge on the capacitor that becomes C dash into V. C dash we calculated here, substitute its value, V that is 100 volt. In the previous example it is given to you, so you will get charge on the capacitor this much coulomb. Now if supply is disconnected and then after the dielectric substance is introduced, then there will be no effect on the charge. So charge that will remain the initial one. So Q dash equal to Q0, and in previous example we calculated Q0, directly substitute its value here. Clear to all of you? Now here energy that is also calculated. So energy, that is Q0 square by 2C dash. Okay, Q0 that we calculated in the previous example, C dash here we calculated, you will get the answer. And the potential difference, that is V dash equal to Q0 by C dash. So you will get the potential difference also. Example 2.10. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? Now see, capacitance of the capacitor given to you, that is 12 picofarad, that is 12 into 10 raised to minus 12 farad. Supply voltage, that is 50 volt. Now energy stored in the capacitor, that is given by the equation U equal to half CV square. So half C, that is 12 into 10 raised to minus 12, V, that is 50, take square of it. Now solve this one, you will get the energy stored in the capacitor. Very simple thing. Example 2.11. A 600 picofarad capacitor is charged by 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in this process? Now see, capacitor with value of capacitance 600 picofarad is connected with 200 volt supply. Now energy stored in this capacitor, that we can write U initial, that is half CV square. We can write it is Q square by 2C also. So half value of C 600 into 10 raised to minus 12. V, that is 200 square of it. So your answer will come to 12 into 10 raised to minus 6 joule. Now here suppose the charge deposited on the capacitor is considered Q. Now this one is disconnected from the battery and connected with identical another capacitor. Which one is initially uncharged? So here equal distribution of charge will take place. So energy stored in capacitor 1, that we can write U1, that is equal to square of charge upon 2C. Charge is Q by 2. So its square, that is Q square by 4 upon 2C. And the same energy will be stored in second capacitor. But Q square by 2C, that is initial energy U. So we can write U1, that is equal to U2, that is U by 4. So the total energy of the system, that is U final, that is U1 plus U2, that is U by 4 plus U by 4. So that is U by 2. U, that is 12 into 10 raised to minus 6 joule. So your answer will be here 6 into 10 raised to minus 6 joule. Now, how much electrostatic energy is lost in this process? So loss of energy, that is initial minus final. So 12 into 10 raised to minus 6 minus 6 into 10 raised to minus 6. So that will come to 6 into 10 raised to minus 6. Clear to all of you?